Hi all. The objective of today's session is to understand positive feedback or split figure circuits. We have an Opamp connected in positive feedback mode with equal resistance. That implies we'll have V out by 2 at non-inverting input implies the feedback is 50% here and the feedback is positive. The moment feedback is positive, we can say that output will be either at plus VCC or at minus VCC. And I have my input connected at the inverting input of the Opamp. So we'll call it as an inverting type Smith trigger circuit. Right? Our objective is to identify the transfer characteristics of the given circuit. Transfer characteristics implies a plot between or characteristics between output voltage and input voltage. Usually, output signal is taken on y-axis and input signal is on x-axis. Right. To begin with, let us assume Vin is at minus infinity, extreme negative value. As my Vin is at minus infinity here implies this signal is greater than this always. So my output will be at plus VCC. When Vin is at minus infinity, I am sure that my output is at positive VCC, right? And if the output is at positive VCC plus VCC here, that will give you my V out, V plus as this is grounded, this is at plus VCC, equal resistors. So my V plus will be this plus VCC divides equally between resistors. So V plus will be equal to VCC divided by 2. When output is at plus VCC, as this is grounded, equal resistors, my V plus will be equal to half of VCC. So if to complete my transfer characteristics, I should plot the V out for entire band of input voltage implies V in varies between minus to plus infinity. So if I am increasing my input towards positive side, this signal towards positive side, until this signal V in signal is less than VCC by 2 plus VCC by 2, output will be at plus VCC itself, right? Plus VCC. The moment input crosses positive VCC by 2, the output switches to minus VCC from positive VCC. It is why because at minus infinity condition, output was at plus VCC that generate a V plus of positive VCC by 2, and the moment negative input crosses that value towards the positive side, this non-inverting input will become greater than inverting, inverting input will become greater than this non-inverting input. So the output should goes to negative. The option for negative output is only minus VCC because it's a positive feedback circuit. then it stays at minus VCC if I am increasing my V in beyond positive VCC by 2 in the positive direction, right? So if the input is initially at minus infinity, initial output is plus VCC, then if you are varying your V in towards positive infinity, you will have a transition from plus VCC to minus VCC at a value V in equal to positive VCC by 2. Then after that it stays at minus VCC always as you are increasing your V in. It's obvious that when V in is infinity, this is positive infinity, extremely large positive value at inverting input. So output should be at negative VCC, right? So we have moved from minus infinity to plus infinity and we got a curve like this. Right. Now suppose the other condition that V out is at minus VCC initially, or the other way, if your V in is at plus infinity initially, V in is at plus infinity initially, a positive infinity at inverting input implies implies a large positive value at the inverting input. So output should be negative. The option is minus infinity. Since it is a positive feedback circuit, output can be either plus VCC or minus VCC. So output will be at minus VCC if my input is at plus infinity. Right. The moment output is at minus VCC, my V plus will be minus VCC will divide equally between these two resistors. So this is my V plus, positive input voltage with respect to ground. So V plus is equal to minus VCC by 2. Right? So V plus is now at minus VCC by 2. So if you are decreasing your input, the moment it crosses a particular value, that is minus VCC upon 2, minus VCC upon 2, then this is minus VCC by 2. If this value, V in value or V minus value goes a value less than minus VCC by 2, this will become larger than this V minus, because V minus is less than minus VCC by 2 and V plus is at minus VCC by 2. So positive input is larger than negative input, output switches to plus VCC. So this will go to plus VCC and it stays at plus VCC if you are decreasing your V in further. So we'll get a transfer characteristics. We will get two arrows here, bidirectional arrows here, unidirectional arrow towards down, unidirectional towards left, uni towards up, unidirectional arrow, right? So this is the transfer characteristics of circuit. Here the parameters of Smith trigger circuit is upper triggering point UTP, lower triggering point LTP, and width of hysteresis low. Upper triggering point is nothing but the value, the highest value of Vin at which there exists a transition at the output side. We have two transitions. One is from minus VCC to plus VCC here, and the other one is from plus VCC to minus VCC here. So the highest value of Vin is plus VCC by 2. So upper triggering point is the highest value of input voltage at which there exists a transition. The transition can be either from plus VCC to minus VCC or minus VCC to plus VCC. Doesn't matter while evaluating UTP. You are looking into the input axis and you are identifying the highest value of the in at which there exists a transition. Transition can be plus to minus or minus to plus, doesn't matter. Similarly, lower triggering point or LTP implies the lowest value or least value of an input signal at which there exists a transition. Transition can be either from plus to minus or minus to plus. Here we are having a transition from minus to plus at a lowest value of minus VCC by 2. Right? Width of the hysteresis loop is sum of this distance plus this one. This is at VCC by 2. This is also at VCC by 2. So sum will be difference between these two. So VCC by 2 plus VCC by 2 or VCC by 2 minus VCC by 2. That will give you VCC. VCC. Right? So these are the fundamental parameters of your Smith trigger circuit. It is a bistable circuit because it is having two stable states, one here and another one here. And the circuit has a memory. Why? Because if this is in state 2, we have to increase our input up to plus VCC by 2 to get a transition from state 2 to state 1. Whereas if the initial state is at 1, then we have to decrease my V in up to minus VCC by 2 to observe a transition from state 1 to state 2. So this circuit output changes for a particular value of V in, and the change in output also depends on the previous value of its own output. So we'll have the circuit involves a memory. So it's a bistable circuit. It falls under the category of a circuit that has memory because the input voltage required to change from state 1 to state 2 depends on the initial value of its own output minus VCC. If initial value of output is state number 2, the V in at which the required transition is positive is 65. Right? Let us observe if I am adding a signal here, DC source here instead of ground, what all are the changes we are going to observe on the transfer characteristics. So let us get into a biased case. I will draw the initial circuit as such. There was an ideal Opamp, positive, negative. This is connected to the in. So this is an inverting type Smith trigger circuit. We had two equal resistors. This was my V out. R and R. Initially, the tail end of input resistance I have grounded. Right now, I will make it as plus 1 volts, positive 1 volts. Okay, and of course, I will have plus VCC and minus VCC here, right? So here my objective is to identify the transfer characteristics as we did earlier, the out on y-axis, the in on x-axis, right? Okay. So as we discussed, if my input is at minus infinity implies this potential will be positive always, then this. So output will be at plus VCC as we discussed earlier. Extreme negative value here implies this is least value negative input. So V plus will be more than that. So output will be at plus VCC. So I will have a positive VCC here, right? So a positive VCC here will give you a V plus. That's a different value compared to the earlier secured because initially it was grounded. Now we have two sources. V out is at plus VCC and the input signal here connected to the tail end of your second R resistor is positive 1. So VCC equally divides between these two resistors. So VCC by 2 plus 1 also divides equally between these two resistors. So V plus you can write it as VCC plus 1 divided by 2, right? So the potential here is V plus equal to VCC plus 1 upon 2. So if you are increasing your input signal towards positive side, to get a transition from plus to minus, your V minus should cross VCC plus 1 by 2 in the positive x direction. So the moment it crosses positive VCC plus 1 upon 2, V minus will become greater than the plus. That implies output switches to minus VCC. So output switches to minus VCC. This is my minus VCC level. So you should be careful about the arrow here. As earlier, this is right, right, towards down, towards right, towards right. Okay. So let us see the other variation. Suppose input is at positive infinity, a plus infinity at the inverting input ensures inverting input is always greater than non-inverting input. So output will be at minus VCC. The moment V out is at minus VCC, you will have a V plus that's equal to minus VCC divides equally. So V plus under this condition is equal to minus VCC upon 2, and this plus 1 DC volts divides equally between resistors. So that will be equal to, I can write it as plus equal to, right? So if your V in is at plus infinity, your output will be at minus VCC minus VCC, and that will give you a V plus signal of negative VCC minus 1 by 2. VCC minus 1 by 2. If your input crosses minus of VCC minus 1 by 2, you will have a situation that your negative input is less than positive input, then output will goes to positive VCC from minus VCC. So if you are increasing your V in, the moment it reaches a value, that value equal to this V plus, this V plus, that is minus of VCC minus 1 upon 2. So this will become less than this V plus value if V in is less than this point, left side of this point. So output switches to plus VCC from minus VCC. Minus VCC. And if V in is extremely small, minus infinity, output will be always at plus VCC as expected. So this is the transfer characteristics of the given circuit if you are replacing a zero potential here ground with a plus 1 DC source. Of course, the direction of your transfer characteristics looks same as earlier, bidirectional down, left, sorry, right, left, up, and bidirectional. The only difference is upper triggering point UTP is nothing but VCC by 2 plus 1 by 2 or VCC plus 1 divided by 2. Highest value of P in at which there exists a change. LTP is equal to minus VCC by 2 plus 1 by 2. Lowest value of P in at which there exists a change. And width of hysteresis loop is nothing but this distance, that is VCC plus 1 upon 2 plus this distance, that is VCC minus 1 by 2. So negative and positive will get cancelled. VCC by 2 plus VCC by 2 will give you VCC itself. So here width of the hysteresis loop remains same as earlier, and your UTP upper triggering point shifts by 1 by 2 units towards right, and your LTP shift towards right by again same 1 by 2 volt unit. So this LTP also shift towards right, UTP also shift towards right. So effectively your transfer characteristics is shifted towards right by 1 by 2 units. So this ended transfer characteristics shifted by a 2 volts, 1 by 2 volts, half volts, 0.5 volts towards right by adding a plus 1 by 1 volts DC. That is because the presence of 1 volts influence V plus by half of the total DC voltage. So 1 by 2 because you are having two equal resistors in the circuit. Width of the hysteresis loop is not depending on the external voltage but the secured parameters. So it remains at VCC itself. Okay. So both case our switch trigger was inverting type because I have applied my input at the inverting input terminal of the panel. So both cases we'll call it as inverting type switch trigger circuit, right? Let us interchange the connections here. Initially, I have applied Vn here and I have grounded here. Let us interchange these two connections. Then my switch trigger circuit will become non-inverting type switch trigger. Positive, negative. Here it is grounded now. R, R, V out. This is my V in, V in plus VCC and minus VCC. Right? So if the input is moved from negative input side to positive input side, we will call it as a non-inverting type switch trigger. Right? Here we'll take different values of resistors. Let us assume it as 4R and 4R and here we have moved the input from negative input side to positive input side. So we will call it as a non-inverting type switch trigger circuit. And we have taken different values for resistors compared to earlier cases 4R and R. So let us try to plot the transfer characteristics of the given circuit. Right? Again, as we did earlier, let us assume extreme conditions to begin with. Let us assume V in is at minus infinity as earlier. If your V in is at minus infinity, this is at 0 volts. Large negative value here, extreme negative value here implies this potential will be always negative. This is at 0 volts, so output will be at plus VCC. Plus VCC. This is my positive VCC mark. This is my V out. There is my V in. So the moment output is at plus VCC, my V plus will be equal to. Now it's divides between R and 4R. So V in divides between 4R and R plus VCC divides between R and 4R. So V plus will be V in divides between 4R and the total resistance is by R plus VCC divides between R and by R. So my V plus will be equal to 4 by 5 times V in plus VCC by 5. VCC by 5. Right. My input was at minus infinity. Expected output is plus VCC. and that will give you a V plus value of this much 4 by 5 times V in plus VCC on 5. If you are increasing your V in towards positive side. Oh, let us do it the other way. Okay, sorry for this. For this. Okay, we have the other circuit here in which I have moved my V in from inverting input to the non-inverting input side, and I have changed the resistors with 4R and R instead of R and R. So my Smith trigger is called non-inverting type Smith trigger circuit, non-inverting type, because I have connected my V in to the non-inverting input. Right. To begin with, let us assume V in is minus infinity. So extreme negative value here ensures a negative value here, negative. So V minus is at 0 volts. Extreme negative value here implies your output will be at minus VCC, minus VCC. This is my minus VCC input. Vn is minus infinity. This will be of course negative. This is 0. Positive input is less than inverting input, negative input. So output will goes to minus VCC. The moment my output is at minus VCC, that will give me a V plus that's equal to, while identifying V plus, we have two different sources here. One is V in, one is V out, that is at minus VCC. So V in divides between 4R and R, minus VCC divides between R and 5R, R and 5R. So I can easily write my V plus as a function of V in and minus VCC. So V in divides between 4R and R minus VCC times is negative minus VCC multiplied by divides between R and 5R, R upon 5R. So that will give you a value V plus is equal to 4 by 5 times V in minus VCC by 5, right? So when V in is at minus infinity, V out is at minus VCC, and if you are moving from minus infinity to plus infinity, your V plus will become positive at some value of positive V in, because right now V in is negative, this V plus is also will be negative. It's clear from the expression that if V in is negative, this term is anyway negative. V in is negative, V plus will be of course negative. So to get a change from minus VCC to plus VCC, your V plus should be positive. That will happen if and only if V in is positive. So to make V plus equal to 0, V plus equal to 0, you can equate your equation, that is 4 by 5 V in minus VCC by 2 equal to 0, implies V in is equal to VCC by 5 here. V in is equal to 5 will get cancelled. V in is equal to VCC upon 4. Right? So if you are increasing your input towards positive side, the moment it crosses a value VCC upon 4, then output goes to positive side, minus VCC to plus VCC, because if input is beyond VCC by 4, its value towards positive side, then V plus will become positive. So output will become plus VCC. And it continues in plus VCC. So transition is towards up, right? So let us move our V in from plus infinity to minus infinity, the other way. Because the split trigger circuit having memory, its new value of output will depend not only on V in but also the initial value of V out. So if initial output is at plus VCC, and if we are moving from plus infinity to minus infinity, plus infinity to minus infinity, let us see what will happen. So if Vn is at plus infinity, this is at plus infinity, implies this voltage will be always positive, greater than 0. So output will be at plus VCC itself. It's a stable state. Then if you are decreasing your V in from plus infinity to minus infinity, what's left? Right now I have plus VCC here. That will give me a V plus value that's equal to that's equal to output is plus VCC. So plus VCC divides between R and by R. So VCC multiplied by R upon by R. And you have V in here. V in divides between 4R and by R. So V in multiplied by 4R by R. So that will give you a V plus positive value, of course, because output is positive. Input I am moving from plus infinity to minus infinity. Right? So this will become V in 4 by 5 V in plus VCC upon 5. So if you are decreasing your V in, at some point of V in, this value will reach at 0 volts, and that value will be corresponding to negative value of V in because all other terms are positive. So V plus will become 0 at some value of V in. So I am equating that V plus value to 0, 4 by 5 V in plus VCC by 5. So this will happen when V in reaches minus VCC upon 4. So this potential becomes 0 when V in crosses a value or touches a value. Its value is equal to minus VCC by 4. That is obvious. This entire term is positive when V in is equal to positive. Then to make it 0, V in should be negative. So that value is minus VCC by 4. Then we'll have a transition from plus VCC to minus VCC. Right? So this is the transfer characteristics of the circuit. The arrow direction is like this, closed loop is like this, anti-clockwise, whereas this was twice, this was also clockwise because it was an inverting type, inverting type clockwise, inverting non-inverting type anti-clockwise direction, right? So let us identify the parameters of my non-inverting type Smith trigger circuit, LTP, UTP, and width of hysteresis. UTP will be is equal to highest value of Vin at which a change occurs. VCC by 4, LTP is the lowest value of Vin at which there exists a change. Change can be from plus to minus or minus to plus, doesn't matter. Width of hysteresis is nothing but this is VCC by 4, VCC by 4. This distance is also VCC by 4. Will give you VCC upon 2. VCC upon 2. Width of the hysteresis loop is at VCC by 2. Initially it was VCC. Right? Okay, let us move to the other case. Here I have used 0 volts at inverting input. I will change to plus 1 volts. So I will do the same circuit with a slight modification here. Let me mark it as plus 1 volts, plus 1 volts, or let me write it as plus 2 volts. Doesn't matter, it should be a positive or negative value. And I'm using same resistors, V out for R, and this is my V in, right? So of course I'll have supply voltages plus VCC and minus VCC, right? So my objective is to identify the change in transfer characteristics compared to earlier circuit. This is my out. Alright, here again, let us assume Vn equal to minus infinity as we did earlier. So if your Vn is at minus infinity, this will be negative, of course. This is a positive value. So output will be at minus VCC, and this is my minus VCC level, right? To get a transition from minus VCC to plus VCC, I should ensure a positive voltage here. So at V out equal to minus VCC, I should identify my V plus, that will be equal to V in divides between 4R and 5R. So we'll have V plus equal to V in as earlier 4R by 5R, and output is right now it is at minus VCC minus that divides between R and 5R, so R divided by 5R. So my V plus will be equal to V in by 5 minus VCC by 5. Here you're having 4 on the numerator, so I'll write it as 4 by 5 V in, right? 4 by 5, 4 by 5, right? So my V out was negative and V in also was negative here. To get a transition, my V plus should cross this value V minus, that is 2 volts now, transition, right? So I have some value for my V in at which I will get a transition. Let us identify that. To get a transition, V plus should reach 2 volts and that V plus equal to 4 upon 5 times V in minus VCC upon 5. That implies, taking the LCM, 10 equals 4V in minus VCC, or V in equal to 10 plus VCC upon 4, or VCC plus 10 by 4, right? So the moment V in reaches a value that's equal to 10 plus VCC, 10 plus VCC by 4, I'll have V plus is equal to 2 volts. So beyond that, V plus will be greater than V minus, so output will goes to plus VCC. And if V in is plus infinity, of course, if this is plus infinity, this will be more than 2 volts. So it stays at plus VCC forever, right? If we are moving the other way, if your input is at plus infinity, my output will be at plus VCC, because a large positive value here implies a positive value that is greater than 2 because V in is infinity. So V out will be positive VCC. So at which I will have a V plus that's equal to, V plus value will be equal to, the only change is minus VCC will become plus VCC. So V plus will be V in as earlier into 4R upon 5R. Instead of minus, I should write plus VCC multiplied by R upon 5. And V in is extreme positive value. VCC is also positive. So V plus, that's equal to 2 volts. V plus 2 volts, that's equal to 4 V in by 5 plus VCC by 5. That implies 10 minus VCC by 4 will give you that V in value, right? So if I am decreasing my input, then if your V in value becomes 10 minus VCC by 4, 10 minus VCC by 4. This 10 minus VCC by 4 need not be negative always, but we should take care. It will be negative if VCC is greater than 10. So if VCC is greater than 10, this will go to negative side. If VCC is greater than less than 10, it will be in the positive side only. So you can assume it either ways. Let us assume VCC is less than 10. VCC is less than 10. So this will be positive. So the moment V in takes a value, V in takes a value that's equal to 10 minus VCC by 4, 10 minus VCC by 4. The output will switch to minus VCC. So I'm taking 10 minus VCC is positive, right? So I will slightly move x to left. This went up here. This was bidirectional. This was out. Like this. I will mark it as 10 minus VCC by 4. And there was a right arrow here, right arrow here, right arrow here. I will extend my y-axis to here, right? And this is my minus VCC point, right? There was a right arrow, up arrow, left arrow, down arrow, bidirectional arrow. So I have a bidirectional arrow here, here, down arrow. So the direction of hysteresis loop is anti-clockwise here. Same thing I am expecting here, anti-clockwise, because my smooth trigger is a non-inverting type smooth trigger. And as we discussed in the last three cases, my LTP was negative, negative, negative. Here it is positive if VCC is less than 10. So in general, your LTP need not be negative always, right? Can be either negative or positive. Similarly, your UTP also need not be positive always, can be either positive or negative. The only point is that UTP will be greater than LTP. That's it. So you'll have both positive, both negative, and LTP negative and UTP positive, not the other way. Your transfer carrots can be here or here, centered at origin. This is LTP, this is UTP, LTP, UTP, LTP, and UTP. Here both are negative, here both are positive, and LTP is negative, UTP is positive in this case. So all three categories are possible, both negative, both positive, L positive, UTP, sorry, LTP negative, UTP positive. LTP negative, UTP positive, not the other way. Right. Out of 4 combinations, you'll have 1, 2, 3 valid combinations. Okay. Right. So properly selecting here VCC value, you can move your transfer characters towards left or right, or symmetrical about y-axis, or right side of y-axis, or negative y-axis. So let us see the values of LTP and UTP here. That is obvious. LTP will be 10 minus VCC by 4, positive or negative depends on the VCC value. UTP here 10 plus VCC by 4 depending on negative or positive values of VCC. And width of hysteresis loop will be difference between these two, right? This is x1, this is x2, or this is x2, this is x1. Width is x2 minus x1. That is 10 plus VCC upon 4 minus 10 minus VCC upon 4. that will give you 10 by 4. 10 by 4 will get cancel each other. VCC by 4 plus VCC by 4 will give you VCC by 2. As earlier, VCC by 2. VCC by 2. So the width of hysteresis loop is not changed. It is now VCC by 2. If you are moving V in from here to right, and LTP and UTPs are changed from VCC by 4 and minus VCC by 4 to some other values, VCC by 4 plus 10 by 4 minus VCC by 4 plus 10 by 4 due to the addition of this 2 volts source. Okay, so adding a positive source at your inverting input terminal is shifting your entire transfer characteristics. When this is 0 volts, this was the characteristics, it shifts towards right, shifting towards right. That is obvious. Initially you have to make it 0. At present you have to make it 2 volts. For that you have to apply more positive value of V. So that's why it is shifting towards right. Right. So we have discussed all 4 varieties of bistable circuit. Remember that this is stage 2, this is stage 1. Both are stable states. To transfer from 2 to 1, you have to travel up to this point. To make a transition from 1 to 2, you have to travel up to this point. So both transition points are depends on the initial outputs. So it's a bistable circuit because it has 2 stable states.